Good day, everyone. Today I'm going to speak with you about nucleophilic addition in either acid or basic media. So you're going to use a weak electrophile to amend to weak nucleophile to amend to a strong electrophile. So, but under basic conditions, that weak nucleophile, just imagine being protic like not isopropanol, but ethanol here. So you just have some generic base that picks up that hydrogen, a protic hydrogen. So you have its conjugate base form. Okay. And then introducing your electrophile. That alkoxide anion is going to react with that ketone carbonyl rather, and then you're going to have a hemiacetyl anion form. This is going to be negatively charged, and then it's just going to pick up a hydrogen from that base that initially removed the hydrogen from your nucleophile. Okay, so I'm going to go back with the base, and that hydrogen has protonated your alkoxide anion formed from this pi bond jumping up to become a lone pair, a third lone pair about oxygen. Okay, so that's just a general base catalyzed nucleophilic addition. Now an acid catalyzed, so base catalyzed, you're constantly going to be following a negative charge. So let's just say for the sake of argument, this is a negative charge. It's going to jump around from one species to the next, right? And then that B minus is going to be there, right? So in other words, starting and ending, you're going to see the same species. Now let's look at acid catalyzed. What that's going to do, instead of making the nucleophile stronger, is actually going to make the electrophile more electrophilic, or at least the carbon. Okay, so now we're going to take that electrophile. In this case, this is just going to be acetone. Picks up some hydrogen, say from H3O. Okay. So in other words, the catalyst is acting as a proton transfer facilitator, if you will. Okay. So the first step, you have a protonated species here. Okay. So what that positive charge is going to do, since oxygen is more electronegative, is going to draw more electron density away from that carbon, further activating it. Okay, so if we have a weak nucleophile, just like we had before, and we don't make it stronger, it can actually amend, right? Because this is the electron-rich species, this is the electron-poor species. Okay, and then these electrons are going to come up. And once again, we're going to have a hemiacetyl group, inevitably. Okay, but this is going to be positively charged as an intermediate. And then there's going to be a second, or we could also say that there's going to be water that can come around and act as a base to remove that hydrogen, more likely. Okay. So what is that going to do? That's going to, in effect, form the same thing we have up here, but just with H3O that gets conserved from the start. Okay, so both things lead to the same, or both approaches lead to the same product. One might go slightly faster than the other in overall span of time. It just depends on what kind of acids you're using versus bases, right? So if you're using a base in this particular instance that is not irreversible, right? If you're just using, let's say, OH minus or something like that, it's going to bounce back and forth from, being this alkoxide anion and say water, and then those conjugate acid base pairs. Okay, so this, you see a little bit of a difference there. So you have a competition really with that OH2 reacting as opposed to this this carbonyl, or sorry, not carbonyl, but alcohol reacting out. Okay. Now what you've seen before, at least on the previous submodule that I went over with you, base catalyze, in particular cyanohydrogen formation. Okay, so that's going to require a base because that hydrogen, about hydrogen cyanide, is going to be in the way of that carbon being nucleophilic. Okay. So in other words, just trying to react this out with a ketone, for instance, is not going to work. So in other words, you're going to need to deprotonate by some means the base, right? So in effect, you're going to get Cn minus. I'm just kind of draw that turned around. Right, so Cn minus, that carbon's going to be nucleophilic. Attack and kick those electrons up. And once again, you're going to have your cyanohydrin. This is just going to pick up hydrogen from that base. Okay, and then once again, base in its negative form, like from the start, is going to be carried over all the way to the end. And you have your cyanohydrin species. It's not going to be stereospecific in this particular case, again, because you just have regular old acetone. All right, so if you wanted to further functionalize this particular cyano group, let's say to a primary amine, you just use H2 and say platinum or palladium. So this is going to be a metal catalyst, and basically it's going to wedge these two hydrogens on sort of in concert and break up that pi bond, so the two will go on in a syn addition. Okay, so not once but twice, so I just write 2 times. And then you'll get this particular construct. All right. Now, in terms of acid catalyze, this can happen not once but twice. And I'll show you how that is done. Okay, so we're going to kind of go about things sort of redundantly. Instead of having, let's say, OH2 so this is a ketal formation. Again, this is going to be under acidic conditions. So instead of H3O as a general acid, we're going to use tosic acid. So tosic acid is going to activate this this carbonyl here. Okay, so we're going to have that attack first. I'll redraw this so it's not so messy. Okay, so some conjugate base of an acid basically picks up that hydrogen and pushes these electrons back to where it's going to be uncharged. Okay. Now, in lieu of our hemiacetal, so that means half of a ketal, this picks up a second proton from tosic acid. So again, this acid is, say, picking up from hydrogen here on this step. Okay, so now we have water as a formidable leaving group, positively charged, so it's pulling electrons away. And intramolecular reaction occurs, booting it off. So now we have essentially this 5-membered ring that's protonated on one side. And then water is going to be around just to pick up that proton. And there you have it. You have your ketal formation as shown on figure 5. So that's just sort of the gory details. Okay, so it's not just one but two additions of ethylene glycol there that are forming this ketal, so that 5-membered ring. Okay, the next transformation up is imine formation or shift base formation. So again, we're just going to take some generic ketone in this case. Okay, so if we have some kind of amine, say a primary amine of some kind, and then we use a weak acid. So this is shorthand just for acetic acid, so nothing special. Okay. But a small amount of this is going to protonate that ketone. Okay. And then this moderate nuke is going to add itself to that carbonyl. There's a tetrahedral intermediate here. Positive charge now about that nitrogen. Put a generic R group. Okay. And something is going to behave as a base, or I'll just put conjugate base of an acid here, just generically. Okay, so now we have this intermediate. Okay, so let's say here. So this OH group, which is not going to be a good leaving group until it picks up another hydrogen. So now that's going to be a positively charged species. Okay, so remember that lone pair is there. So that lone pair comes down and lends itself to this carbon that's more electropositive because this is drawing electron density out. It's going to kick that water off. That's going to be important because we're going to think back to what that means if we're trying to reverse things backwards. Okay, so this is going to be positively charged. Now let's say that water. I'm going to pick up that hydrogen, or maybe an acetate group, whichever. A little more likely just an acetate group. Let's put that A- there, whatever. Okay, so then we're going to have a neutral species and we have a Schiff base that is formed. So one thing to note here is that once again, if you form an imine, which is what this is, if these two groups that were initially about this ketone and it were asymmetric, then you would have a mixture of E and Z isomers. Remember that this is going to have low priority and this is going to have higher priority. So whatever it is with respect to the highest priority about this carbon is what it's going to be, either E or Z. Okay. So that's something to think about. Again, so I'm just going to draw the transformation here. So I went through the nitty-gritty with this mechanism. But if you wanted to reverse it, hey cat, shh, be quiet. So if you wanted to reverse it, you just use water and a little bit of acid and it would kind of work in the reverse, right? So in other words, you would do what is referred to as hydrolysis to remove this. And so you just kind of play around with the conditions to revert backwards. So this is in reverse. So if you didn't sponge up that water that gets formed at this step, and it's still kind of lingering around in the reaction, that's the difficulty you're going to face. Okay, so an enamine formation. So that, or enamine, rather, you're going to have a Schiff base that forms. But instead of having that CN double bond occur, an enamine, or an enamine rather, is going to have a secondary amine as opposed to a primary amine for that nuke. So what you're going to have is an intermediate. You can imagine all the steps that I went through with you for the previous mechanism, the Schiff base formation. Sort of like with your enolates, where the ene comes in, right? So that hydrogen that's there, you're going to have that second, amino, oops, or secondary amine work as a base. This positive charge is going to pull those electrons over, right? And then you'll have a enamine as a result. Okay, so this is an enamine right here. Enamine. Okay, for all my enamines out there. Okay, so once again, same, go through several steps like you saw before. You have that leaving group of water, right, that gets protonated. Again, this is still going to be under weakly acidic conditions. So that's something also to remind yourself. The reason why it's going to be under weakly acidic conditions is, remember that this is going to be basic. At least weakly basic. So in other words, you don't want too much of that acetic acid to be in the solution, or otherwise you'll get a protonated form. Okay, the next conversion, at least in figure 8, involves hydrating a nitrile with water to an amide, primary amide. Okay, how does that work exactly? Well, you can imagine this being a nucleophile and a bunch of proton transfers happening. Okay, I'm not really going to go over the mechanism with you. I just want you to be aware of this nitrile to amide conversion or transformation. Okay. So again, just with regular old water. Okay. Reason being is that this is this carbonyl, or sorry, that carbon is going to be fairly activated because this is going to be a very polar bond. Also, just to give you sort of an idea, I made a fatty acid version of this nitrile when I was working in industry, and it was very important that we kind of capped it off when we were done synthesizing it. In other words, we had to keep it under nitrogen and then pretty much put it into ampule form, because if you let any type of moisture, otherwise in Memphis it's pretty abundant, any type of moisture that would get into that ampule would drive the reaction in reverse. So actually what we did was we went in reverse and applied Le Chatelier's principle to go from amide to nitrile. Okay, so there's some kind of industrial process for that. I'm sure you could, look it up. Okay. All right, so the next conversion we'll refer to is something I've already introduced to you, which is Wolff-Kishner. Okay, so it is the same sort of theory applied with a shift-based formation, just with a hydrazine. Hydrazine is actually going to be even more reactive than a primary amine. Okay, so essentially, in your notes, you can look at the mechanism on page 907, but I'm just going to kind of go over the basics here with you. Okay, so the first step is with hydrazine and that's N2O4, typically rocket fuel. Okay, and that's going to be under acetic acid and ethylene glycol. So what that is going to provide you with is what is referred to as a hydrazone. Okay. All right, so once again, you can have an E or Z isomer of this. But what's going to happen is if you treat this under strongly basic conditions, as KOH, not KO4. All right, so it's under strongly acidic, basic conditions with the application of heat. So what that's going to do is actually drive off this to become N2, right? So these hydrogens are going to get stripped off. It's going to form N2 irreversibly. So N2 in the gas phase, plenty of it around us, right? And then this will become basic. So what it's going to do is you're going to have one negative charge after another as hydrogens are getting removed, and eventually you're just going to have this particular anion, right, that is just going to be basic, right? It's going to be under basic conditions, and it'll probably just pick up that last hydrogen from, let's say, water, right? And then you'll just have your aldehyde that you started out with become a CH3 group. So in other words, full reduction. Okay, so these are pretty harsh conditions. Again, you're going from mildly acidic to strongly basic. So in other words, that pH is going to shoot right up between one step and the next. And again, in that particular set of conditions, you're going to have an E2 mechanism. So that N2 is going to be the, I guess the part that is being eliminated, but this is going to be your leaving group, right? So that it'll be like your eliminating scaffold right there. Okay. Again, take a look at page 907. And that'll have all the mechanistic explanations you'll need. I'm not going to particularly quiz you upon this. I just want you to know the actual transformation and what kind of media you would look to avoid if something is particularly, let's say, base labile. Okay, so moving on. We're going to get into carbon-carbon bond formation via aldol condensation. So in other words, we're going to go with a symmetric aldol condensation. So we'll use NaOH as our base. So we're going to form an enolate. And as a result, we're going to generate a resonance hybrid So here's the enolate form. you have a second equivalent of, let's say, acetaldehyde like we had before, push that guy back down. These electrons are going to come out. Push these electrons up. Okay, so in other words, turn this thing around here. Okay, so negative charge. This picks up a hydrogen from, say, that water that you generated from the first step here, right? Let's say water comes off there. Then it comes right back and acts as an acid in this case. So that is going to be simple aldol condensation. And the naming is just about as literal as you can get. So you have aldehydes that are condensing, right? And as a result, you're forming an alcohol, right, from that addition. Okay. Now, there are some cases in which conjugation will drive this OH and then this hydrogen right here to become dehydrated. In other words, there's going to be a certain type of mechanism that's going to drive that, which is referred to as E1CB. So that means elimination unimolecular conjugate base. Okay, so I'll do this now just with crossed aldol condensation. So this is two species that are the same, identical, that are condensing, as opposed to right here where you have a mixture of different aldehydes that are condensing. Now it's going to be one particular product because this doesn't have a hydrogen to remove. This one does, right? At least an alpha hydrogen. So again, let's say that OH takes that hydrogen away. Okay, so I'm just going to skip a step, just draw things in an enolate form like how I did below there. Okay, so again, lone pair drops down. And you're always conserving a negative charge here. So put pH right there. Okay. This is going to pick up a hydrogen from water again. Not any different than what we saw before. Okay, so we're almost seeing the same kind of Same kind of thing as what we saw below, right, with that not crossed or symmetric aldol condensation. What's going to happen here now is that since this needs to be eliminated in order to jump from a conjugated system, so in other words, this is going to be a phenyl ring, right? So what's going to break up the pi system right here and the pi system that's right here? Something that's begging to be a pi system right there in the middle. Okay, so in other words, conjugation is going to drive this particular mechanism. Okay. So if we pluck off this hydrogen from OH minus, remember we're still under basic conditions and that base is going to be there from that last step. So electrons are going to go up and they're going to essentially seesaw back over to knock that OH off. Right? So we typically don't think of OH groups as being good leaving groups at all. Right? But again, conjugation is really going to drive this particular mechanism forward, kicking everything off. So in other words, you're not going to see a protonated form of OH to leave and typically be seen as a good leaving group, right? But you're going to get a highly conjugated system. I'll draw pH now. That's phenyl. Okay, so just to show that that's all now one pi system instead of two pi systems split up by sp3 carbons. Okay, so that's what's really driving this type of product formation. Okay, now moving on to kinetic versus thermodynamic enolates. You have a choice of bases you can use. Both are strong, the first being OH minus, so that's just the textbook classic example. You have, in other words, NaOH or KOH versus LDA, which is something you're going to be you would generate in situ or in the situation. Okay, so in order to generate this, you would want to have it under low temperature. Okay, so in other words, it isn't just taking protons just at will from all over the place. Okay, also, you want to keep it under low temperature because it would be explosive to use. Years ago, there was some poor woman that was working alone in the lab and generated that in a syringe, and it ended up catching her lab coat on fire, and she basically got cooked to a crisp with that. So, yeah, you have to use some pretty wicked caution with that and not expose it to air at all. All right, so in other words, you're going to be using low temperature for LDA. So while you tend to think of kinetic versus thermodynamic enolates tend to form a thermodynamically stable product as opposed to kinetic, which is going to form the fastest product. So the way you can kind of keep these straight is thermodynamic is enolate is something you would just use at room temperature or at an elevated temperature, and then LDA is something you would use at a lower temperature. Okay, so the first thing you do is, at least for this top particular example, you have OH, it's going to strip that hydrogen off. Okay, so as a result, you're going to have an enolate formed. Okay, and this is going to be a kinetic enolate, or sorry, thermodynamic enolate. Okay, so it's going to be more substituted. Notice also that OH minus is going to be much smaller, so it can actually grab onto that particular proton and pluck it off. Okay, so this negative charge is going to sway back and forth between that carbon there and that oxygen. So the nucleophile is essentially here and going to branch out and attack your electrophile, which is right here. Okay, so I'll just shorthand that as pH. Okay, so it comes along, boop, pops up your pi electrons over there to become a third lone pair. Okay, and then try to get this as brief as possible here. So you have now a quaternary carbon. Okay. And then this is going to be basic enough where it's going to pick up a hydrogen off of water. Not like anything you haven't seen before. Okay, so you're going to have that particular alcohol. Oops. All right, and that's pretty much it for your thermodynamic enolate. For your kinetic enolate, this is going to be too bulky to just pluck off, well, what particular hydrogen is it going to pluck off here? If you were to try to react this out, it would not pluck off this particular hydrogen, it would pluck this hydrogen off here, because this is the closest or fastest hydrogen that it can reach. So in other words, that's going to be a kinetic enolate that you would generate over here. Okay, but more importantly, LDA tends to pick off hydrogens that are part of a methyl ketone, like in this particular instance. So let's just say there's a lone pair of LDA, negative charge, pick up that hydrogen there, and you'll have an enolate that'll form. Sorry, I'm running out of space here. I'm trying to keep this condensed in as to the point as possible. Okay. So we have, again, an enolate that can go back and forth, resonate back and forth with this CO double bond, so it's going to sway back and forth. Which carbonyl is it going to attack for the second step? So the second step means you're going to apply an additional equivalent of this para-substituted ring here. So it's going to attack the least sterically hindered. In this case, it's going to be the aldehyde. Okay, so space. Okay, so sorry about the tight spot here. I'll just erase this. Okay, so again, that aldehyde is going to be more reactive than your ketone over there. It's going to pick up that hydrogen. Or this alkoxide anion is going to pick up that hydrogen. Okay, so you'll have your aldol, but remember that since that's going to go to an alcohol here, I'm going to erase this portion. You can always scroll back on your trusty little stream there. And remember that you're still going to be under basic conditions. Still going to have things under basic conditions here. So OH, or sorry, this isn't going to be OH. I'll just use, my apologies. Okay, so we'll just use generic B for base. Remember, this is still going to be under LDA conditions, right? So we take that one hydrogen. Those electrons are going to go up and then cascade back down to initiate an E1CB mechanism. Again, conjugation is going to drive the dehydration of this particular reaction. So all right, so now that we have this ion here, collapses back down, actually pushes these electrons over, so it kicks off that OH, at least that's how it's theorized. And then you're going to have a dehydrated product. But again, this is pretty much disturbed from this sp3 environment here in order to be a full sp2 or mostly sp2 portion of the molecule. Okay, so two different portions are need to be bridged together, and what's going to drive that is a dehydration. Okay, so that's your final product there. Sorry if things look kind of disproportionate, but this is the site of disconnection that you see there. Okay, so if you refer to figure 11 in your notes, this is going to be an intramolecular reaction. So an intramolecular aldol condensation, in other words. Okay, so you're going to form a thermodynamic enolate. Again, you can just show as resonating back and forth here. It's a resonance hybrid. Not really going to change too much in terms of what's going on. Hello, kitty. Okay, so lone pair comes back down, kicks these electrons over. So it's going to form a 1, 2, 3, 4, 5-membered ring. Okay, so we'll have the ketone there, as it were. And oh boy, this guy right here, yeah. So that's where the negative charge winds up. Here's where the disconnection site is. Okay, so now this picks up a hydrogen or proton from water that would be generated from the last step, from the first step rather. Okay, so we're back into a basic environment. Hello, kitty, again. We have this OH group. Okay, so we're still under acidic, or sorry, basic environment here. So that OH minus is going to pick up this hydrogen. Oops. And you're going to have a conjugate. Form here. So that those two electrons are going to come back and again boot this off. Okay. Okay, so what I'm looking to show you here is that this point of disconnection right here. Right, so there's conjugated sp2 geometry right there between where this condensation occurred and where that original ketone is. Okay. So again, that's the point of disconnection. All right. Last thing to cover conceptually before we go over a couple more problems and mechanisms is Robinson annulation. So in your notes, I said that the reagents needed are an alpha beta unsaturated carbonyl with 2 acidic alpha hydrogens, and then a ketone / aldehyde with 1 acidic alpha hydrogen. Okay, so the particular example that I gave you in figure 12, notice how I kind of earmarked all those carbons with 1, 2, 3, 4, 5, 6. So you're forming a 6-membered ring. All right, so the first connection that you're going to establish is the enolate from let's just say you use LDA. Okay, so when this comes back down, this is going to react out with, I'm going to draw this right over here, my other substrate here, which again, this is going to have 2 alpha hydrogens. It's going to have at least 1 alpha hydrogen. So, and this is, sorry about that. And then these electrons are basically going to cascade over. I have to listen to that every day too. Yeah, so anyway, we have now, I'm just going to shorthand and write this pH here. Okay. All right. Now, this is going to become pick up a hydrogen. Almost say. Very little of it anyway. And it's going to revert to a ketone, right? Because it's going to form an enol, but it's going to revert back to a ketone, or the keto form, because that's going to be the most stable. Okay, so then the base comes around again, picks that hydrogen off. Okay, so then you get an enolate from that. Okay, and that's going to be an intramolecular reaction now. So it's kind of a 2-step series. First stop is you're actually generating an enolate reacting out with an alpha beta unsaturated ketone. And then once that bond has been established, you're going to cyclize. Okay. So I'll just put things back down in a linear format. So put that up. Okay, so a 1, 2, 3, 4, 5, 6-membered ring. Beautiful. Okay, it's going to kick this up. A pi bond up to where it's going to be is that right? Yeah. Okie dokie. So this carbon here is what? Oops. Just drew a charge there. Just going to earmark right there with an asterisk. Okay, so it came around, popped this up. This is going to pick up a hydrogen, right, from the conjugate acid of the base, whichever base we're using. Okay, so this is going to be an alcohol, right? It's going to be a tertiary alcohol, but again, since this is going to be under basic conditions via E1CB, that is going to drive this off, water off, and then you're going to have what you see on the right hand side of your figure 12 there, just flipped over, right, is your annulated product. Okay? So in other words, a ring formation. Okay. Last thing I wanted to just discuss with you is reductive animation. So essentially you just form a shift space either with ketone or aldehyde and then reduce with sodium borohydride. So it's a two-step process. So let's say we have 2-butanone. We act that out with, let's say, methylamine in the presence of acetic acid. So we're going to get E and Z isomers of this imine. And if we just treat that with something delicate like NaBH4, sodium borohydride, in the presence, let's say, of ethanol. Okay, that's just going to reduce this down to secondary amine. Okay, so if you wanted a primary amine in lieu of this, you would just use, let's say, NH3, okay, or just ammonia. Okay, so this is going to be and again, this hydrogen is going to come from the proton of ethanol, and that hydride is actually going to be what's going to amend to the carbonyl. Okay, so this is going to be a racemic mixture as a result. All right, so we'll go over a couple of problems here, and then we'll wrap things up on this particular module. Okay, so 1880, page 941 in your text. So this is a lithium cuprate reagent. Remember, that's going to amend whatever alkyl, one of the alkyl groups that are hanging off of it. The organic metallic compound. It's going to go conjugated addition. So in other words, from the first step, you're going to get this particular compound. So it's going to be R and S 50-50. Remember, this is going to be planar. And then the second step for 2, this is just going to be under Wolff-Kishner conditions. Your book doesn't really write it, but you're probably going to need some kind of acid catalyst to drive that forward. So what that's going to do is form a hydrazone with that particular carbonyl, and then that OH, in addition to applied heat, is going to basically strip off all the hydrogens and make this carbon basic to where it's just going to pick up hydrogens elsewhere. Okay, so the transformation there for the second step is going to be just something that is non-stereospecific. In other words, methyl cyclohexane. Okay. For B, so using this particular aldehyde, reacting it out with NaOH. So presumably a half concentration. So you do aldol condensation. I'll write what that's going to look like here. So 1, 2, 3, 4, 1, 2, 3, 4. Okay, good. And then treating this particular molecule, so that's the first step. The second step is going to be basically reducing that aldehyde to an alcohol with NaBH4. And of course, use ethanol for the protic hydrogen there. So that's what you're going to get. All right. So pretty straightforward. It may seem like some of this carbonyl chemistry is pretty redundant, but the devil's sort of in the details here. So I would pay attention to what kind of functionality or two substituents or two different types of reagents rather that you're combining, and seeing whether or not conjugation is going to drive E1CB, etc. So of course then we're going to get into this next submodule. We're going to get into synthetic strategy. So it's another thing to think about when you're trying to establish carbon-carbon bonds or reducing carbonyls and things like that. All right, so everybody have a good one. See you next time. Thanks.